Hello everyone, in this video I am going to show you how to perform operations on 4 of the test signals and performing of DFT and using Hilbert how to perform operations on a signal. So initially in this thing I am taking FS as 900 and then the time domain time scaling is this thing and then the length of signal I am taking is N here. X is my signal which is FM signal. So for here I've taken the signal with 3 frequencies. One is with 20, other is with 40 Hz and other is with 60 Hz. I've just added by dividing it in time domain. Initially I've taken 1/3 of the signal with frequency 20 and other 1/3 with frequency 40 and the other with 60. Now after that we'll get X, a frequency modulated signal. The frequency modulated signal, after obtaining it, performing of DFT on frequency modulator, all this is not required, but if at all you want to perform DFT computation, then here this is the process you do it. And Hilbert transform directly gives us the DFT. So here after DFT we do Hilbert. Instead of doing all this process, we can directly use the MATLAB command Hilbert to get the Hilbert transform of the signal X. After that, to obtain the instantaneous phase and frequency, these are formulas that I use. So here we'll just see how instantaneous frequency varies. This is so let us see how instantaneous frequency of a FM signal varies. And let's see. See, this is the instantaneous frequency. This is the signal obtained in the imaginary part of Hilbert transform, and our initial frequency modulated signal is this one. See, you can see 20 Hz, 40 and 60. The variation can be observed clearly. So this is how we calculate instantaneous frequency from a FM signal and how to just make an FM signal. Now going to the second test signal. This is the exponential signal. I've taken Fs here to be 1500 and the similar way the time division, and after that the signal, I've taken the signal as exponential here. This is my signal and on that I perform the Hilbert transform, and similar is the process for calculating instantaneous amplitude. This is the formula. I have said is nothing but it just calculates the magnitude and gives us the magnitude of the signal. We can also calculate the decay rate here using this formula, and all this is nothing like it can be used for performing the average of the decay rate because the decay varies. So let us observe how instantaneous amplitude is of an exponential signal. So this is how you can see it. The blue color one is the exponential signal that I have taken, and the instantaneous amplitude is the red border that you see. You can even do it in this way. So this is how the instantaneous amplitude varies of an exponential signal. Now going to the third test signal. This signal is basically the 1 by 1 plus t square signal. Here I have taken Fs to be 1000 and the time I have taken in both positive as well as negative axis, n is the length, and the signal is 1 by 1 plus t square as you can see, and on the same thing I have performed Hilbert. And after Hilbert, we'll just observe the signals, how it will be. So let us just check it. See, in Hilbert, as we can see, the zero crossing point is obtained at the peak. So in this way, identification of peaks gets easier. This process gives us a feasibility in identifying the peaks in a signal and performing the processing on it. Similarly, now let us go for the fourth test signal. It is the same way. I've taken the signal with different amplitudes and same frequency. Initially, I've taken test one signal is same signal with same amplitude but different frequencies. Here the signal is with different amplitudes and same frequencies. So here in the same as the first test signal, I've just changed the amplitude with frequency remaining the constant. I've taken 3 as my frequency, constant frequency. So this is the frequency that I've taken, and the amplitudes are 0.4, 0.2, 1 and 0.3, 0.6 and 0.8. We can just observe the signal. We'll just observe the signal. So this is the signal I've taken, the signal with different amplitudes but the same frequency. Now on this, when we perform Hilbert, and plot it by taking imaginary part, we'll observe the same thing that we observed in the test signal 3, that is the peak will be obtained at zero crossing point. So let us see it. So here, as you can see, at peaks we are getting a zero crossing point. At all the peaks there is a zero crossing point at all the peaks. So this is the basic and main use of Hilbert function. To identify the peaks is really easier, and that is all we can perform on the 4 test signals. These are the test signals for today. Thank you.